Ladies and gentlemen, thank you for joining us today in this webinar organized by Anand and hosted by Carrie. My name is Xiaojing Guo from Tsinghua University in China. Today, I have the privilege of moderating this meaningful webinar as a member of Anand Steering Committee. First, I would like to give a very brief introduction to Anand, the Asian Network for Education in Nuclear Technology. Anand was founded in 2003 with great and sustainable support from IAEA, the International Atomic Energy Agency. During the past 20 years, Anand has been dedicated to the noble cause of sharing nuclear knowledge and resources among its member countries in Asia and the Pacific region, to build regional partnership in capacity building and human resource development and knowledge management. Besides, Anand has been running an online platform to manage and preserve nuclear knowledge. Just like our slogan says, this is where we share nuclear knowledge. To kick off this webinar, I would like to introduce our distinguished speakers today, Mr. Sun Choi and Dr. Kwang-Hun An. Mr. Sun Choi brings more than 40 years of R&D and management experience at Korea Atomic Energy Research Institute, KERI, to his role as the former vice president of small reactors development. He led KERI's efforts to develop, design, and verify the technologies related to Korean small water-cooled reactors, such as the Smart Reactor, SMR, and the domestic PWR, APR 1400. He is striving to get a leading edge with the various technologies combined. Mr. Choi earned a master's degree and completed a PhD course in mechanical engineering at Seoul National University. He has served as a member of ASME and KSME and Korea Nuclear Society. Dr. Kwang-Hun An is principal researcher in Smart System Development, Korea Atomic Energy Research Institute, KERI. And Dr. An currently leads a mechanical design group for SMR at Korea Atomic Energy Research Institute. He has participated in the various stages for development of SMRs, including the SMART, the innovative S-SMART, and the ISMR. He received his master and PhD degrees in mechanical engineering at KUST, Korea Advanced Institute of Science and Technology in 2008 and 2013, respectively. He is also a member of KSME and KNS. I'm sure we will gain a deeper understanding of SMR from these two presentations. Next, let's welcome Mr. Choi to start his presentation. Please.
Thank you for your very kind introduction for me and Dr. An. Hi, wonderful participants. I'm Sun Choi. Me and Dr. An will guide you through today's webinar, Innovative Nuclear Power, Small Modular Reactor. I'm delighted to connect with you from various countries across Asia. To kick things off, I would like to share a short clip that introduces our esteemed organization, KERI.
For a safe society where people feel safe. For the healthy and happy life of everyone all the time. For a new growth engine of national development. The Korea Atomic Energy Research Institute conducts research so that dreams can come true and everyone can live a good life.
In short, My organization, Korea Atomic Energy Research Institute, was established in 1959 by the Korean government and is the only R&D institute in Korea dedicated to sole nuclear energy. It has been a birthplace of Korea nuclear technology, achieving localization of PHWR and PWR fuel plants and many nuclear-related R&Ds. As a prologue to our webinar, we will begin with the critical topics of climate change and energy. Let's explore the interconnected dynamics between these two vital aspects. We face numerous global challenges as we strive for a better future. In 2015, all the United Nations member states unanimously adopted the 17 Sustainable Development Goals to catalyze positive transformation worldwide. The SDGs are shown in the slide, and they cover a broad spectrum, ranging from eradicating poverty to promoting gender equality, ensuring clean water and sanitation, and fostering economic growth. Additionally, the goals underscore the need to combat climate change and preserve ocean and forests. These goals serve as a collective roadmap for fostering peace, prosperity, and sustainability for both people and the planet, both now and in the future. For more in-depth information on each goal, you can explore the United Nations Sustainable Development Goal website. Within the framework of 17 SDGs, the International Atomic Energy Agency, IAEA Atom for Peace program plays a crucial role in contributing to and supporting the achievement of 9 goals from number 2, Zero Hunger, to number 17, Partnership for the Goal. Among these goals, we will be focusing on 3 directly related to energy: Goal 7, Goal 13, Goal 19, Goal 9, Industry, Innovation, and Infrastructure. It is evident that having sufficient, affordable, and clean energy with a specific emphasis on nuclear power plays a pivotal role in addressing and achieving these interconnected and essential sustainable development goals. What is energy then? Let's see the energy and the nuclear energy some more. Energy, in simple terms, is the capacity to do work. It manifests in various forms and has the ability to transform from one form to another. Some key forms of energy are in the slides. These different forms of energy are interconnected and can be converted from one form to another, demonstrating the dynamic nature of energy. Also, we can divide the energy into man-made versus natural. Moreover, you shall see the sun is the primary source of all natural energy. Here's a concise breakdown of several energy sources: fossil energy, renewable energy, and nuclear energy. Each energy source has its unique characteristic and impact, and understanding this distinction is crucial for making informed decisions about sustainable energy use. In recent time, various regions across the globe have been experiencing more frequent and severe weather events and natural disasters. The consensus among experts and specialists is that this surge in abnormality can be attributed to the excessive emission of greenhouse gases from the burning of fossil fuel. To overcome these challenges and ensure our survival, it has become imperative to transition towards sustainable and clean energy solutions. Thus, we need sustainable clean energy to jump up the greenhouse gas hurdle. This slide underscores a critical point. The primary driver of climate change is closely tied to energy-related activities. A substantial 73.2% of greenhouse gas emission as of 2016 originated from the energy sector. This includes a broad spectrum of activity like power production, heat utilization, and transportation. As civilization continues to develop and the economics grow, the demand for energy in the form of power production, heat, and transportation is expected to rise. Acknowledging this reality is crucial as we explore sustainable solutions to meet the increasing energy demand without influencing climate change. Germany's energy mix provides valuable insight into the challenges associated with transitioning to renewable energy source. With the emphasized how Germany still relies significantly on non-renewable sources with emphasized renewable energy. The combined proportion of gas, coal, and lignite exceeds that of renewable energy, standing at 45% compared to 44%. This reliance on non-renewable sources is partly due to the intermittency of renewable energy. To compensate for the fluctuation of renewable energy production, backup sources like a coal plant are necessary for the consistent and reliable energy supply. Now let's see the characteristic of nuclear power and the classification of reactors. Understanding these characteristics and classification is essential for compensating the diverse application and consideration in the fields of nuclear technology. As you already know, there are two reactions to generate nuclear energy. Those are fission and fusion. Fission is an atom splitting phenomena, while fusion is an atom combining phenomena. Both produce amount of energy by E equals mc squared. Nuclear fusion use lighter elements such as hydrogen and helium, which are in general more fusible, while the heavier elements such as uranium, thorium, and plutonium are more fissionable. Let's delve into the unique characteristic of nuclear energy, considering both the positive aspect and the challenges it presents. While nuclear energy offers certain advantages in terms of low greenhouse gas emission and high energy density, addressing challenges related to radioactive waste, safety, economic viability, and proliferation risk is crucial for the sustainable and responsible use of nuclear power. Striking a balance between harnessing its benefits and mitigating its drawback is a complex task, that requires careful consideration and ongoing advancement in technology and policy. Nuclear energy can play in the global effort to combat climate change and achieve decarbonization. In the table shown, you see life cycle CO2 emission from nuclear is 2 to 60, extremely lower than the others. It emerges as a crucial element in the toolkit for addressing climate change and realizing ambitious decarbonization goals. Let's look at the characteristics some more. Absolutely, the high energy density of nuclear fuel is indeed incomparable to many other sources, making it a standout feature of nuclear energy. The energy ratio is a million times higher than the chemical reactions such as burning fossil fuels. While the high energy density of nuclear fuel brings many advantages, it's important to manage the associated challenges, such as the safe handling and disposal of radioactive waste to ensure the overall sustainability and responsible use of nuclear energy. The issue of nuclear waste is complex and often surrounded by misconception. Fact is, it's the smaller amount and controllable. The high energy density of nuclear fuel means that a relatively small amount of fuel can generate a large amount of energy. With the proper management, including the careful handling and disposal of nuclear waste, radioactivity can be controlled for a limited period of time. Radioactive materials decay over time. This figure, where radioactivity reduces to 100th over 100 years, illustrates the concept of decay and the decreasing impact of radioactive substances over time. Risks associated with the radioactive waste are sometimes exaggerated due to the facts of invisibility and imperceptibility, lack of understanding of dose, exaggeration of plutonium risk. This point is well explained by Professor Miller in his book of Energy for Future President. According to Wiki, over the past 50 years, there has been 10 accidents rated at INES level 4 or higher, showcasing the relatively low frequency of serious nuclear incidents. In the 70 years since the development of nuclear power, the reported number of direct deaths due to nuclear accident is less than 70 people. This emphasizes the effectiveness of safety measures and continuous efforts to improve reactor design. The number of deaths from hazardous chemicals is highlighted as surpassing the number from the nuclear accident. While acknowledging that nuclear power plants are not risk-free, the statement emphasized that they are not more dangerous than the other accidents inherent to civilization. A recent and substantial challenges in deploying large nuclear power plant appears to be of economic nature. Examining the table, the LCOE, levelized cost of electricity for nuclear power is around $70 per megawatt hour, seemingly competitive with any other energy sources, particularly renewable. However, the perception of nuclear power being expensive arises from the substantial total construction cost, a significant investment with a prolonged construction period of 7 to 10 years, inclusive of licensing permits. In the case of large nuclear power plant built in the West, for the past 10 years, construction cost and construction periods are very unstable, as shown in the table. Westinghouse Vogtle power plant has had its construction period extended by 5 years, with the construction cost more than doubling. Framatom's Olkiluoto is showing a more than threefold increase in construction cost and the 13 years construction period extension. However, this is not necessarily the case. The construction period and construction cost for the Baraka nuclear power plant exported to the United Arab Emirates by KEPCO Korea were the same as planned. Since this uncertainty is large due to the large scale of business, the concept of SMR, a Gen 4 nuclear reactor, is being proposed as a way to utilize nuclear energy while avoiding this issue. However, the implementation of SMR is still in the developmental stage, necessitating verification through construction and operation. In this context, proliferation, nuclear energy is like two sides of the same coin. In the crucial aspect, nuclear materials from nuclear power plant carries the potential for diversion into weapons of mass destruction, including atomic bomb. Now let's go into the classification of nuclear reactor. Primarily, nuclear reactor can be categorized into various types based on generation, ranging from the first to fourth, considering factors like size, neutron utilization method, application purpose, and the type of coolant and moderator constituting the reactor. This classification is presented in the accompanying table. Okay. The generations of nuclear power plant. Beginning with its first commissioning in the 1950s, the first generation marked the initiation. The second generation from the 1970s encompasses the early models of light water and heavy water reactor, including the notorious 3 Mile Island and Chernobyl plants. The third generation, emerging in the 1990s, represents nuclear power plant with enhanced economic feasibility. Following nuclear accident, the 3.5 generation, featuring new safety concept, emerges around 2010. We are in between 3.5 and fourth generation. Looking forward, the new generation, the fourth nuclear reactor, aims for improvement with innovative concept related to safety, economic feasibility, nuclear non-proliferation, and nuclear fuel utilization, with plans for construction starting from around 2030s. There's another non-PWR plants, reactors, the Gen 4. representing the fourth generation nuclear reactor, deviates from the use of live water as a coolant or moderator. Indeed, it employs very fast coolant, including sodium-cooled fast reactor, very high temperature reactor, gas-cooled fast reactor, molten salt reactor, supercritical water-cooled reactor, and red-cooled fast reactor. Operating at elevated temperature, this aims to enhance efficiency and effectiveness utilizing metal, salt, or gas as a coolant. In the mid-20th century, before the 3 Mile Island and Chernobyl accident, nuclear power energy operated comfortably, maintaining its traditional advantage. However, the nuclear era witnessed a decline following these accidents. Now there is a pressing need to explore challenging new ways to address the global issues of climate change, leveraging innovative technology. This is a prologue, end of prologue. And now, from now on, let's take a closer look at SMR. SMR, Small Modular Reactor. There's a word SMR. Recently, you may hear a lot if you have a bit interest in nuclear power. What is SMR? SMR stands for Small Modular Reactor. Small means physically a fraction of the size of a conventional nuclear power reactor is 1/10. Modular, systems and components to be factory assembled and transported to a unit to a location for installation. You can understand it when you recall Lego block. Reactor, harnessing nuclear fission to generate heat for energy. That is, the advanced reactor that produce electric power up to the 300 megawatt built in the factories and transported as modules to utility and site for installation as demand arises. Early time reactors were all small in power, but are not SMR. The driving forces behind the development of small modular reactor include modular and safety from passive safety systems and inherent safety features, and multiple application and robust siting provides much flexibility. Remember the words modular, passive, and simple safety system, robust multiple application for SMR. We are aware that SMR stands for Small Modular Reactor. Additionally, S stands for Simple, Speedy, and Safe in Technology. M stands for Manageable in Economy. And R stands for Resilient and Responsible in Climate Control. From here, my colleague, Dr. An, will give you information of worldwide SMR development.
Okay, hello, I'm second speaker, Kwang-Yan An. Following Mr. Choi's lecture, I will introduce two chapters. The first chapter covers the current status of global SMR design, and while the later discusses suggestions for R&D topics required for innovative SMR design. As depicted on this map, most countries with nuclear technology are actively developing SMRs, indicated by the colored countries on this map. Each country have various purpose for developing SMR, such as achieving carbon reduction goals, replacing old thermal power plants, and meeting off-grid demand. According to a technical report from the IAEA, there are currently over 70 SMR designs in development worldwide. The majority of these developing SMRs belong to the light water reactor type, which also constitutes a major portion of commercial reactors. As of now, only 4 SMRs in China and Russia are in operation, with an additional 4 in Argentina, China, and Russia under construction. And 2 SMRs in Korea and the United States have received design certification. One is the SMART in Korea, certified in 2012, and the other is the NuScale in the United States, certified in 2020. The other SMRs are currently in the conceptual or basic design phases. Today, I'll briefly introduce some representative SMRs among the over 70 designs available. The first one is the NuScale nuclear power plant by Nuclear Power Company in the USA, featuring a unique and innovative design in the field of nuclear energy. With an electric power of 60 megawatt, which is comparatively lower than the other SMRs, NuScale gains a strong advantage in compactness. Its smaller dimensions enable easy transportation by train, making it suitable for construction in inland areas. This SMR is designed with integral type. That means all the major components, such as steam generator and pressurizer, is installed inside of the single vessel. Notably, the reactor coolant system operates through natural circulation, eliminating the need for a reactor coolant pump. And this SMR operates as a pressurized water reactor. Currently, the NuScale reactor is undergoing the regulatory review by the US NRC. The second one is SMR 160 by Holtec International in the United States, boasting an electric power of 160 megawatt. This is considerably larger compared to the NuScale power plant, leading to the adoption of a block-type reactor rather than an integral type. Unlike the integral type reactor, the block-type reactor separates and connects major components to the reactor vessel. As you can see in this figure, a steam generator and pressurizer are separated from the reactor vessel. Like NuScale power plant, reactor coolant systems in this reactor operate through natural circulation, eliminating the need for a reactor coolant pump. And this SMR operates as a pressurized water reactor. Currently, this reactor is undergoing pre-licensing review from the US NRC. This is the New World by EDF Consortium in France, featuring an electric power of 170 megawatt for each reactor. The key concept revolves around flexible operation utilizing 2 independent 170 megawatt reactor modules. This reactor adopts an integral type, although it has large electric power. So it results in larger reactor and containment vessels compared to the NuScale design. During operation, this reactor is submerged in an underground cooling pool. Unlike previous 2 reactors, the reactor coolant system in New World relies on forced circulation with the reactor coolant pump. This reactor operates as a pressurized water reactor. Currently, this reactor is in the conceptual design phase. This is the ACP100 by CNNC in China, featuring an electric power of 125 megawatt. Adopting an integral type design, the ACP100 has the steam generator and pressurizer installed inside of the vessel, with the reactor coolant pumps connected to the vessel through loaders. And the ACP100 adopts a fully passive safety system, which includes a passive core cooling system, passive residual heat removal system, passive containment heat removal system, passive inhabitation system, automatic depressurization system, and passive hydrogen control system. This SMR operates as a pressurized water reactor. As of now, this reactor is currently under construction. This is a BWRX 300 by GE Hitachi in the United States and Japan, with an electric power of 300 megawatt. The development began in 2018, focusing on scaling down the design of GE Hitachi's 1500 megawatt ESBWR and enhancing safety features. The parent design 1500 megawatt ESBWR received design certification from the US NRC in 2014, but has not been constructed. The BWRX 300 features a natural circulation reactor coolant system without reactor coolant pump. It adopts an integral type design and operates as a boiled water reactor. As of now, this reactor is pre-licensing stage. This is KLT-40S by Rosatom in Russia with an electric power of 35 megawatt. The KLT-40S is based on small nuclear power technology originally developed for submarines and icebreakers, now being commercialized. It is an upgraded version of the reactor used for icebreaker propulsion. Initially designed for combined heat and power generation in isolated regions where power and energy supply is challenging. It also finds applications in desalination and providing power for petroleum production. Manufactured in shipyard, the KLT-40S is assembled as a complete unit and transported to construction sites, minimizing on-site work. The steam generator and pressurizer are connected to the reactor vessel through nozzles. Notably, the KLT-40S has been utilized in the world's first floating nuclear power plant, which commenced operation in 2020. This SMR operates as a pressurized water reactor. There are numerous other SMRs in various stages of development worldwide. As depicted in this slide, these SMRs can generally be categorized into two main types, integral and block. The integral type, exemplified by designs like NuScale, incorporates major components within a single vessel. On the other hand, block type SMRs such as the SMR-160 feature separate installation of components like steam generators and pressurizers. I think now you can distinguish the difference between integral and block types. The majority of currently developing SMRs today are adopting the integral type. Among them is integral pressurized water reactors in particular. Now let's delve into the integral pressurized water reactor in more detail. An integral pressurized water reactor, called IPWR, is a type of nuclear reactor design where all major components, including the nuclear reactor core, steam generators, and primary coolant system, are housed within a single integrated pressure vessel. The primary coolant directly transfers its heat to the secondary coolant within the same pressure vessel, eliminating the need for a separated loop and reducing the number of components and potential leak path. The close proximity of major components simplifies the design and enhances safety by reducing the risk of coolant loss accident. Many observers have noted that the SMR design is integral with all significant primary components inside the same vessel. In fact, as you may already know, block type is also SMR if its electric power is lower than 300 megawatt. The animation on the upper right side illustrates the commercial pressurized water reactor. The red loop within the containment structure is known as the primary system, while the blue loop crossing the containment structure is referred to as the secondary system. The reactor core is situated at the lower part inside of the reactor vessel. In the primary system, the reactor coolant heated from the nuclear fission energy in the core circulates through the reactor coolant pump and transfers heat to the secondary system in the steam generator. The pressurizer in the primary system allows the reactor coolant to reach temperatures exceeding 300 degrees Celsius, maximizing heat transfer efficiency in the steam generator. The coolant in the secondary system transforms into steam in steam generator by receiving heat from the primary system. This steam then operates the turbine, generating electricity. The most severe accident in a nuclear power plant is the loss of the coolant in this red loop, because this coolant passes through the nuclear fuel. This loss of coolant accident can occur if any connection part in this red loop is damaged. The figure on the left shows the actual shape of the reactor in this squared region. In an IPWR, all components such as pressurizer, reactor coolant pump, and steam generator are installed in a single pressure vessel. In other words, the red loop in this commercial reactor is located within the single pressure vessel. So there is no leak point in the red loop in this integral reactor. IPWR has advantages and disadvantages. Advantages are enhanced safety, compact design and reduced footprint, and simplified construction and operations, inherent stability, improved thermal efficiency. And disadvantages are limited flexibility, higher maintenance challenges, complexity in manufacturing, potentially higher cost, and lack of operating experience. Overall, the advantages and disadvantages of the IPWR design need to be carefully evaluated based on specific project requirements, regulatory considerations, and safety assessment. While the IPWR design offers significantly safety benefits and potential advantages in certain applications, it is essential to weigh these against the potential challenges and costs associated with this relatively novel approach. From now on, I'd like to introduce the Korean SMR. However, before delving into that, let me provide a brief overview of the chronicles of Korean nuclear power development. Through this, you will gain an understanding of why Korea succeeded in its SMR development and was able to achieve the world's first design certification. Korean nuclear power technology has progressed and achieved independence through several stages over the past 50 years. It was possible to achieve continuous development by simultaneously advancing technology and domestic construction. From 1974 to 1981, Korea entered a stage of total dependence on foreign technology. The second stage, spanning from 1981 to 1995, marked a partial stage of technological independence using foreign technology. The third stage, covering the period from 1995 to 2009, marked the phase of technological independence. Finally, fourth stage after 2009 is characterized as the stage where Korea has become a nuclear power plant exporter. Currently, we have 25 operational sites and 3 sites under construction and 2 shutdown sites. Currently, 29.6% of the total electricity generated in Korea comes from nuclear power plants. This is the most advanced nuclear reactor in Korea, the APR 1400. This reactor type was developed using Korean indigenous technology and has been exported to the United Arab Emirates. Based on this accumulated nuclear power plant technology, we could develop the Korean SMR, the SMART. This is integral type pressurized water reactor with electric power of 110 megawatt. It can be also utilized for desalination at a rate of 40,000 tons per day. It has design life of 60 years, and it has received the world's first design certification from Korean regulatory body. The left figure shows the SMART. The reactor vessel has a diameter of 6 meters and height of 16 meters. All major components, including the steam generator, pressurizer, and reactor coolant pump, are installed inside the press vessel. The conceptual design of the SMART began in 1997, and it received its first design certification in 2012. Currently, it is undergoing the process of receiving a second design certification for an improved design. It is expected to be completed by the end of this year. Now, let's discuss what should be done to innovate the design of the SMR. Considering SMR concept is not new and has not been commercially deployed for the last 20 years, there are challenges that need to be addressed for SMR deployment. These include, but are not limited to, licensing risk as a technical barrier, comparative economics as a commercial hurdle, and public perception regarding safety and spent fuel management. Again, issues and challenges with respect to technology are such that a licensing issue, because the SMR is the first of a kind structure, system, and components. And non-light water reactor technologies, operability and maintainability, staffing for multi-module plant, and supply chain for multi-modules, and advanced R&D needs. And non-technical ones for industrial, economics, and public security issues exist. In order to promote the licensing and technical verification of SMR, especially IAPWR, R&D needs should be met. They are core flow stability for natural circulation, hybrid engineered safety system development, reliability, uncertainty, and sensitivity analysis for integrated control rod drive mechanisms, PSA for multimodal SMR plants, considering common cause failures, and human factor engineering, control room staffing, and operational procedures for multimodal SMR plants. To make SMR more competitive in the future, they want to apply advanced state-of-the-art technology to the SMR developed. I suggest 8 innovative candidates. The first technology that I suggest is 3D printing, also known as additive manufacturing. 3D printing is being adopted in the nuclear industry for its potential to introduce significant innovations for both currently operating and future nuclear plants. Here are some of the applications of 3D printing in the development of SMRs. 3D printing technology can enhance the design flexibility, enable complex geometry, result in cost savings, facilitate rapid prototyping, and improve material strength. And there is electron beam welding. Electron beam welding is a fusion welding process that uses a beam of high-velocity electrons to join materials together. The electron beam hits the materials and causes them to melt and flow together, forming a weld. Here are some of applications of electron beam welding in the development of SMR. The advantages of ABW technology include the rapid deployment, cost reduction, improved efficiency and quality of welding, as well as versatility. Robots offer an excellent solution for maintenance and inspection in the nuclear industry. Their utilization is increasing, especially in the development and maintenance of SMRs. They provide efficient inspection and maintenance capabilities, remote operation, underwater tests, surface decontamination, health physics tests, and pre-programmed inspections. Furthermore, robots are undergoing development to meet the unique requirements of nuclear environment, including challenges such as radiation effect, remote maintenance, and deployment constraints. The digital twin serves as a virtual representation of an entity, process, or a system. In the SMRs, digital twins find applications in predictive maintenance, information and communication, analysis and integration, control, modeling and simulation, and uncertainty quantification. In summary, digital twin hold the promise of significantly enhancing various capabilities in nuclear SMR development, encompassing information provision, communication, analysis, integration, control, modeling, simulation, and uncertainty quantification. And furthermore, essential technologies that we need to prioritize include the development of new materials, innovative fuels, passive safety systems, and IoT technology. Okay, from now on, Mr. Choi will continue the remainder of this presentation.
Hi, Sun Che again. An energy storage system is a technology used to store energy for later use. Energy storage system stores excessive energy generated during period of low demand and high renewable energy production and release it when demand is high. Now let's dive into the concept of mixed system combining renewable and nuclear to supply energy. The goal of these mixed systems are to take advantage of each energy source, maximize economy through a mix, and contribute to climate action. Let's explore the concept of a hybrid system that combines nuclear and renewable energy, which is referred to NRHES hybrid systems. With the integration of smart grid technology, we can effectively manage supply and demand. The NRE hybrid system should be optimized based on geographical position, climate conditions, and national economic factors. Smart grid is also a brand new idea for the control of grid using IoT technology. It can effectively manage both the demand and supply of power within the grid by communicating with each component. This IoT application enables optimized management and make it feasible to create hybrid combined energy system and that manage flexible power supply. Smart grid technology provide to be highly efficient, particularly in the small microgrid settings. Achieving energy use efficiency can be utilized through the diversification of utilization method and application areas. Beyond the electricity production, considerations for thermal usage in the industrial heat and district heating, desalination, hydrogen production for various transportation, and provision of propulsion power should be explored. This approach not only contributes to address climate change, but also expand economic feasibility and market opportunities. Reflecting on the global SMR development landscape, out of approximately 70 developing new SMRs, there aren't many from Asia, however. However, several Asian countries are actively pursuing energy independence and economic growth through the adoption of SMR. Notable Asian countries in the world SMR development status include Korea, China, and Japan. According to 2017 data, Asia's share of the global SMR market shows demand in the Middle East, Near East and Southeast Asia, including China and India. Potential markets for SMRs are site, regions, countries with reduced to less needs for large transmission lines. There are archipelago countries in the Southeast Asia with isolated populated area and limited grid that may need distributed generation, which is suitable for the SMR deployment. So, for Asian countries with small grid and without natural gas, SMR could be viable option. In considering the deployment of SMR in Asia, the following top-tier requirements should be prioritized. It is required that, number one, low carbon energy. Number two, advanced safety features. Number three, modularized small-scale generation capacity. Number four, energy security and independence. By meeting these top-tier requirements, SMR can effectively address the energy needs to the Asian countries, contributing to sustainable development, energy security, and meeting the demands of evolving global energy landscape. This slide shows the Nautilus Institute's SMR report on Indonesia, and it highlights significant challenges and concerns regarding the deployment of SMR in the near future. These are absence of tested SMR designs, regulatory requirements for use of proven technology and on-land site, higher electricity generation costs associated with the SMR technology, public opposition to nuclear disaster, lack of support at higher level of government, requirement for domestic providers participant in the energy infrastructure. While these concerns pose challenges to the smooth deployment of SMRs, it is essential for stakeholders to collaboratively address and find solutions to ensure the successful integration of SMR into the energy landscape. Acknowledging and mitigating these concerns will contribute to the sustainable and effective implementation of SMR technology. Don't miss nuclear power plant deployment involves a collaborative efforts from various stakeholders, each playing distinct roles, from government to public. We propose the following measures to our fellow Asian countries based on Korea's successful experience. First, conduct comprehensive feasibility studies. Second, develop a clear nuclear energy policy. Third, invest in human resources, skilled workforce, and infrastructures. Fourth, prioritize safety and security. Fifth, engage with the public and stakeholders. Sixth, explore international cooperation. It is essential for Asian nations to carefully consider these factors, adopting a cautious and well-planned approach. This will enable them to maximize the benefit of nuclear power while minimizing potential risks and challenges associated with the initial deployment, particularly in the case of small modular reactors. Now, I will summarize today's webinar. SMR, small modular reactor or nuclear energy, is an attractive option to solve climate action and to enhance energy supply security. There are various world's SMRs from concept to licensing, no operation yet. Innovative SMR concepts have common technology development challenges, including regulatory and licensing frameworks. Learn the benefits from coupling with renewables to stabilize the power grid. Asian countries have great potential to SMR deployment. Thank you for joining us today. Thank you.
Thank you, Mr. Choi and Dr. Allen, for the comprehensive and excellent presentations about small modular reactors. Actually, this presentation has 3 parts: different generations of MPP, SMR, and energy storage system. So now we have a question and answers time for our participants to raise questions if you have any. You can also input your questions in the chat box if you have a chat box in your screen to write your answers. Or you can just raise your hands and ask. Yes, please. Mr. Desigree, can you hear me?
Yeah,
Please.
okay. I'm Dikri from Indonesian, and I'm like to ask about the SMR about the small modular reactor. What is the efficiency of the reactor? Because as we know, as the last PWR of our pressure water reactor, we can reach about 40% about efficiency. So I want to know how high the efficiency about the SMR. Thank you very much.
Okay. Conceptually, SMR PWR plant, IPWR, has almost the same efficiency as the large PWR, which is a 34 or 35%. But you know that the SMR adopts the natural circulation. So the overall efficiency of the plant is a little bit lower than the forced circulation plant. But, you know, avoiding that efficiency drop reductions, we use different multiple applications for the heat generation or the desalination or any other application purpose combined with electricity generations. And also for the Gen 4 reactors, which is non-PWR type, operates at a very high temperatures. The efficiencies are quite high, 50 to 60%. Is that an answer?
Thank you very much, Professor.
Anyone else who wants to ask questions? Mr. Choi, can you see any questions in the chat box? Because here on my computer, I cannot see the chat box.
Oh, okay. I need some time because I'm an old man with the stress.
Too many
Yes.
buttons.
Uh-huh.
Any updates on my possible?
Oh, yes, we have a question, huh? Mr.
Oh.
Amarijargal,
Amari.
can you hear us?
Hello, can you hear me?
Oh, Miss, please.
Yeah. Thank you for the presentation. I have one question regarding to the SMRs are in operation. You said there are 4 reactors are in operation. So I'm curious that reactors are in like integral type or the block type. Was my question clear? Can you hear me?
Yes, I can hear you. Your question was operate the reactor type in operation, right?
Yes. Like
Okay.
in your
Block type
presentation,
or
it says there are like 4 reactors in operation. So I'm curious that is that the type of the reactor is integral or block type?
Yeah, okay. And operated reactor in the Russia is block type. That's KLT4S. And as I know, the other one is HCP100 in China. That is integral type, right?
Oh.
Yeah.
So which means that like we are like gaining like more experience data on like both types, right?
But the operation experience is quite short. I mean, the block type starts its commissioning in 2020. So, and I know that the ACP 100 from China is not yet in commissioning yet. So actually, there's a very limited data.
Oh, I see.
IWR of the block type.
Okay, thank you.
There is a question about the updated roadmap for SMART from the Unico A. Batista. And actually, Korea now has a roadmap for another SMR which is called ISMR. ISMR, Integrated Innovative SMR. And SMART has some difficulties with financing problems. And also, you know that Korea is a very small country, highly electrified. So we have a very limited site, plant site here in Korea. So for the prototype plant like Smart, we have site problems and we have some funding problems. So we don't have any concrete updated roadmap for Smart right now. That's an answer to your questions. Okay.
Thank you, Professor.
Additionally, now we are trying to export the smart still. The contact countries Canada and I forgot, but anyway, we are trying to export the smart. Yeah.
We have a raised hand from Mr. Gani. You can turn on your loudspeaker.
Hello and greetings from China. Thank you very much for the comprehensive presentation. My question is to kindly ask for more information. Is continually developed, and digital technologies are also helping to improve operations and maintenance of the nuclear power plants, especially the SMR now that it is also upcoming. So regarding modeling and simulation, information about data analytics and also machine learning and
Excuse me. I think the signal is not very good and we cannot hear you clearly.
Oh, okay. I'm sorry. Maybe the signal is bad, but I've sent in my question in the chat box.
Okay, thank you.
Or use email for more information. It will be much helpful for us to discuss that kind of questions. Please use email then, lately.
Okay, thank you very much.
Thank you.
Please share the email. I can contact you first. Thank you.
Okay, thank you. Mr. Choi, can you see more questions in the chat box?
I see the questions from Ehsan Torabi. Ehsan Turabi. And the question is, can you consider my advice to the roadmap of deployment of SMR in Asian countries? Yes. We have a very good experience, I think, that to adopt the nuclear power program in Korea for the last 40 years. We do our self-reliance programs for the large nuclear power plant from the very beginning to the self-reliance of the nuclear technology. So follow the steps we had in our roadmap of nuclear power plant self-reliance. It will be very helpful for you to set up such a plans. So my advice is, I think, will be good for you. And the second one is
No experience in construction.
If a country has no experience in construction of large traditional nuclear plant, you think that the country can deploy SMR technology? Yes. SMR construction and the design of SMR isn't that different from the traditional nuclear power plant, large nuclear power plant. And the country has no experience means just a beginner. So you cannot do the whole 100% of construction or the design at the first stage. So follow step-by-step increase in the self-reliance program. So you can do the same thing for the large power plant and also the small power plant. Just follow the more developed countries or the more developed vendors to cope with the self-reliance or the construction or the deployment of the SMR. That will be the way to do that. So you can do it in the same way. That's my answer. What is the EPG of? Okay. There is another question. Joseph Tugo. What is the EPG of SMART? The EPG of SMART is inside the site boundary, which is about 800 meters from the reactor. But, you know, EPG is defined in the law and the regulations. So we do not just apply the 800 meters of EPG right now for the current regulations. But the calculated EPG of SMART is 800 meters.
And there is question about the progress of the reactor CAREM-25 in Argentina. Actually, this reactor is comparative reactor for us, so we have very limited information. So we don't know exact progress of this reactor.
Many SMRs are planned to accommodate its application to the military use, I think, for the aircraft carrier or the submarines or any other military purpose. So sometimes the information is quite bad to the public. So Argentina started its current 25 project some 25 to 30 years ago, but you know the information isn't that transparent and to the public, as far as I know.
Okay, we still have 2 minutes. Maybe if there is no question in the chat box, we can also put an end to today's webinar.
If you have questions that is not answered today, please contact me by email. Then I will make very sincere answers to you.
Thank you. Thank you, Mr. Choi and Dr. An. This is a very successful webinar. Thank you very much, and I wish you a good day. And please continue to pay attention to Carrie, to ANAND, to IAS activities. We will hold a series of webinars in nuclear area in the future.
Thank you so much for the good presentation.
Thank you for joining us today. You're having more questions?
I wrote down my email address in the chat box.
Oh, okay, to share. Actually, we have one raised hand from Nitis. Please. There's no sound, huh?
Can you please now unmute your mic? It is someone. I have allowed.
Sorry, we cannot hear you.
Can you hear? Can you hear my voice?
Yes, now we can hear
Thank you. I have actually I have two questions, but I will ask one by one. So you have mentioned that a small modular reactor use new materials. Can you explain or share what type of the new material? And the second question about research and development for small modular reactor, you have mentioned. As I read that I didn't see that you have research and development program for the material reliability. Material reliability, especially material for pressure vessel. Could you explain or could you explain in more detail about the type of new material and the research and development program for material reliability, especially material for pressure vessel? Thank you.
그다음에 해결료하고.
Actually, your voice was not clear, but as I understand your question, the new material means if the material for the reactor is very limited because we have to use reliable material for the reactor. But if we adopt another material, for example, more higher strength material or something like that, then we can make lighter reactor or a smaller reactor, and the other one is material for the nuclear fuel, right? Yeah, but actually, my major is not about fuel, so I cannot explain in detail. But if you give question by email, I can transfer your
Yes.
question to the expert.
Okay.
덧붙이실.
I will ask because especially for the material preservation, there are many type of material, and also the compatibility material between base metal and weld metal. Okay, I will ask you through email.
Email.
Okay,
Okay.
Thank you.
Yeah.
Thank you.
Thank
Thank you for your
Thank
attention.
you, Stefan.
Yeah, I guess that's all. Yeah, Sauzi?
Yes, please.
Yeah, I think it's all. So I think we will end the meeting now.
Yeah, sure. It is
Yeah.
3 minutes
Sorry.
after. Okay.
Yeah.
Thank you for your attention, and I will see you in our next webinar. Thank you, Mr.
Thank
Choi,
you. Thank you.
Dr. and see you. Bye-bye.
Thank you.